So when I first saw this question, I saw the quadratic first, and I wanted to complete the square. And I'm not saying that's the only way to do the question, or the best way to do the question or something. That's just honestly what I thought when I saw this question. I guess I met quadratics earlier on than I met logarithms, so I'm more comfortable with manipulating those. But equally, if you're good at logarithm facts, then you might have spotted logarithms first. So now I've got this logarithm, and I started thinking about how this quadratic inside. I'm still thinking about the quadratic. This quadratic inside x minus 1 squared plus 1. Well, that's bigger than or equal to 1. I'm using the fact that squares are positive. So I suppose I know that this is logarithm of something that's bigger than 1. That means that this is positive, I think. I've finally used a fact about logarithms. Okay, does that help? It helps a bit, but 3 of these functions are positive. I suppose this never runs into the problem of being log of 0, so I never have something like this where it does a sort of log spike thing. Okay, so not C, not D, because they've got this kind of asymptote or point where it's not defined. Whereas I'm pretty confident that this is well defined and nice for all values of x. Okay, then I'd probably try plugging in values next, I think. So next I'd say, well, I know that this takes its minimum value when x is equal to 1, and that value is, if I really think a bit, is log 10 of 1, which is equal to 0. And okay, this means it actually gets all the way down to 0. The only one that looks like that is E. Okay, so not A and not B. Well, B looks quite similar to E, but I'm not quite in the right place there for the minimum. Okay, and that's not the only approach. People in chat have suggested looking at finding the derivative, or thinking about the logarithm first, or thinking about the minimum of this function from kind of first principles. I guess that's what the derivative approach is looking for. Or plugging in other values, using the fact that this is log base 10 to think about, well, maybe can I make this into a nice value somewhere else? Okay, lots of ways in. This is fantastic. So my first job is I need to draw sine x. Here we go. Okay, I've drawn my axes. That's a great start. Sine looks like this. Oh, that's not bad. I'm quite happy with that. People who have been here since ages ago will remember that early live streams were done drawing with a mouse. Everything was awful. Now things are just quite bad. Okay, so this is sine x. And it's reflected in the line x equals 180 degrees. That's here. Okay, 2 methods of what happens next. One method would be to just draw what happens when it's being reflected in this line, and then try and identify what we get. So it's going to come down and up like this. I'm thinking about what's going on over there. I'm thinking about what's going on over the other side. This is 180 degrees. So it's got this bump going around and then under and then up again. And then squint at this and say, oh, hang on, I know this function. This is minus sine x after doing that reflection. Alternative method for this part is to think about that reflection as a transformation of graphs. So if you like thinking about reflections in terms of reflections in terms of functions, then the thing you might write down is sine of 360 degrees minus x, which is equal to minus sine of x. Okay, cool. This is the equation for how you do a reflection. And then I can use some sine facts to work out what that's equal to. Okay, either approach works. Okay, next thing we're going to do is we're going to reflect it in the line y equals 2. Here's me trying to imagine that. So now I'm reflecting it in the line y equals 2 is way up here, right? Way up here. And when I reflect it, this bit's going to turn over and go really high. Okay, so I guess I'll get this bit up here. And this started as a good picture, and now I think it's actually quite a bad picture. Yeah, no, it's gone really bad. I'm trying to imagine this upside down because it's been reflected in this line. Y equals 2. And I'm completely failing to draw it upside down. But I'm also trying to draw it kind of far away from this dotted line as well, right? Because this dotted line, the mirror symmetry line, is way above this curve. Okay. Question, I suppose, is where has the middle of this curve gone to? So the middle before was at, it went through the origin. I check where that point goes to. So when I reflect that point, I go up. So it's 2 units below the line, and afterwards it will be 2 units above the line. So it'll be at 4, believe it or not, on my sketch. Goodness me, that's a terrible picture. Okay, I think what this means, oh my word, this is awful. Okay, I think I'm calling it now. I think this might be the worst picture I've ever drawn. I think that means that this is 4 plus sine x. I think this looks a little bit like sine x. I've mangled it badly, and it starts at 4 instead of 0. I'm sort of heavily inspired by that being one of the options, and it's got the number 4 at the start. Okay, maybe that was how you attempted this question, but maybe not. Maybe you had a different approach in mind. Someone in chat says, I'm terrible at drawing things, and I tried to show you some algebra to do, and then I sort of wimped out of doing the algebra. I guess the next step would be to write down the way you reflect in the line y equals 2 is you do 4 minus the previous thing you had. This is how you reflect in the line y equals 2. It's a bit weird that you put sort of double the number in. I guess that's what this question is testing, that when you do a reflection you put in the equation for how you do a reflection uses kind of double the number. Okay, so there's 4 minus sine x, and that's 4 plus sine x. Okay, there's a sort of algebra approach to doing the question. Okay. There's only got a few kind of key features, I suppose, and then I guess a lot of the way this is marked at A level or something is we're looking at key features and looking for properties of your graph. So for example, here we'd be checking to see, for this graph we'd be checking to see, do you understand that when x gets close to A, that's a problem. The values get really large. This has got some sort of asymptote. And you might sketch that by drawing a dotted line, or you might draw the function getting, you might draw the graph getting pretty large. Sure, okay. Do you understand that when A is minus, when x equals minus A, this is 0? Normal way we might mark your graph is we might look at some key facts like this. I'm not saying that these are the most important things. These are the first 2 things I've spotted. We might check whether your graph does something like this and whether it looks about right. So here my graph, oh my word, I'm now going to draw a terrible graph to prove a point, I suppose. I wonder if it would be a good idea to write this as minus what? What is this? So this is, I'm wondering if I should rearrange this a little bit and try and pull out a factor to say that this is, this is x minus a plus 2a over a minus x. Well, I've written that very carefully because I'm thinking about pulling out a minus 1 to write it like this. Maybe that's helpful because now maybe I can think about that as in terms of scalings and moving the thing around. Anyway, it turns out that it goes through 0 at minus a. It gets really huge at positive a. And I think from this way of writing it, I think it's clear that it's just going to get bigger and bigger. It's an increasing function. I would not try to differentiate this. I think we don't have the techniques at level of maths to differentiate that function. Of course, you might be able to differentiate it because you might have seen, I don't know, the chain rule or something, but I'm going to try and not assume the chain rule thing. Cool, something like that, I think. I'm not sure if it's got gradient 0 there. I'm not sure if I care either. Cool, that's my picture anyway. Here's the villain's lair, and I'm going to try and explain the setup here a little bit more. So it's a semicircle because it's a hollowed out volcano. The other half of the volcano is all still full of molten lava, so that's really dangerous. But this half of the volcano has been hollowed out, and it's got these bits on the side that are shark tanks. So these are terribly dangerous. They're full of sharks, and it's got this bit in the middle, which is safe to stand on. That's some sort of platforms or covers over the top of the shark tank, but they're rigged to move backwards and forwards in a complicated system of pulleys and switches and levers. Let's try and draw a shark. That's exactly what sharks look like. There we go. Terrifying. Okay, complicated system of levers and pulleys to move these covers backwards and forwards, according to the value of theta. The question is, we want to find the area of this bit where it's safe to stand in terms of theta. Okay. Suggestion that I saw in chat was to draw in these two radii. I think that this angle is theta, and also this angle is theta. I think so. This is sine theta along here. These radii are both 1, and then something brilliant happens. That means that this angle here is a right angle. Because this is 90 minus theta, and then this is 90. Hooray! Okay, that gives us a way to find the area of A. I'm going to think of A in terms of some a quarter of a circle, 1/4 of a circle, plus 2 triangles. Okay, if that makes sense. Two triangles, quarter of a circle. Quarter of a circle, I can write down the area of that, and that's 1/4 of pi r squared. R is 1, and then the triangles have area. I guess this is cos theta, this is sine theta, cos theta, sine theta over 2, plus another cos theta, sine theta over 2. So the area of A is 1/4 pi plus cos theta, sine theta. I think, if I've got the area of a triangle right. I feel like we did something like this a few weeks ago. Somebody look back through the archives, find have we done a proof like this before? I feel like we might have done a proof like this before. Here's how I would do this. Here's what I want to show. And on a scrap of paper or something, I'd write down what I want to show. I want to show that sine theta cos theta is less than or equal to 1/2. Well, what do I know to be true? So I know that sine squared theta plus cos squared theta equals 1. So I've got to find some sort of thing that relates these items together. You know, I've got to find something that relates the thing I know with the thing I want. The first thing I thought of was, aha, here's my idea. I'm going to take sine theta plus cos theta and square it. Because you see, I've recognised that these are square terms, and then this looks like the kind of cross term that I get when I multiply out a square, and there's even going to be a 2 in there somewhere. So I'm going to multiply this out. Okay, brilliant. Okay, sine squared plus, this is going to be this square is going to have loads of these terms in. That's kind of my sentence. And I know that squares are positive, so I know that this thing on the left is going to be bigger than or equal to 0. Okay, so if I write that out, I get sine squared theta plus 2 sine theta cos theta plus cos squared theta is bigger than or equal to 0. And then I know sine squared plus cos squared, so I get 1 plus 2 sine theta cos theta is bigger than or equal to 0. So I get sine theta cos theta is bigger than or equal to minus 1/2, which is not what I was asked to prove. I've got a minus sign in there, annoyingly, and I can't just fix it by throwing a minus in. Okay. I can't just take minus of each side. So this is my first idea. My first idea hasn't worked. So now what I'm going to do is try and adapt my solution, to try and adapt my proof, to prove something subtly different. Here's what I've seen. The experience of writing this out has shown me that, this kind of feels like almost like the right idea, but I've got some minus signs around as well. This was quite powerful though. It meant that squaring this thing gave me a way to say, well, this is positive, so we'd deduce a fact about sine theta cos theta. And after messing around a bit on a bit of paper, I found out that something else I could do would be to take sine theta minus cos theta and square that. I mean, that's also positive. So this is a kind of new, separate, true fact. Sine minus cos squared is bigger than or equal to 0. And you see, if I multiply that one out, I did a few of these, but then I found that this one, that minus sign comes through here, and that really helps me out, because now I have 1 minus 2 sine theta cos theta. It's bigger than or equal to 0, which is exactly what I want. Sine theta cos theta is less than or equal to 1/2. Okay. So I would now take this bit, and I would write it up, and I'd put some words in there, and I'd explain what I was doing. I'd write it up as my solution. I'm going to add in some words to try and make this into more of an explanation. Okay. So just to show you how I do that. So I'd add in something like, oh no, dearie me. I'd say we know that, and I really would literally, I'd come back afterwards and write words in, because when I'm just doing maths, I don't explain it to myself with words on the page. So I'd write this because, I'd add it in because squares are positive, that's the relevant fact here, and then I'd put in so, this thing, and then I go so, probably, or something like that. And then I might even write as required. I might not bother actually. No, I really can't be bothered to write as required. That feels like a waste of time. The person marking it knows what was required. I know what was required. Can't be bothered. Right, okay. We've got this area A, and we saw before that the area of A, so I haven't really started the question yet, I'm just writing down what we had before, was I think pi over 4 plus cos theta sine theta. Okay. So the area of B, I suppose we want, if we're going to talk about this ratio, we might like to talk about the area of B, and I guess we should talk about the area of the entire hollowed out volcano. That's half a circle, so that's pi over 2. This is going to be pi over 2 minus pi over 4 plus cos theta sine theta. Okay, so this ratio, this fraction, is pi over 4 plus cos theta sine theta over, what is this? This is pi over 4 minus cos theta sine theta. Aha! So, we want to make this as big as possible. This looks a bit like a plus x over a minus x, where a is pi over 4 and x is cos theta sine theta. And we saw in part 1 that we can make that function really big by making x as big as we want, as big as we can. We saw in part 1 that we want to make x as large as possible. Okay, following, so we use part 2 here for the area of A. We use part 1, we saw that we want to make x really large, to make this function large, it's an increasing function. So we want cos theta sine theta to be as large as possible. And then part 3 tells us how to do that. Part 3 says that cos theta sine theta is less than or equal to 1/2. And in fact, if theta is equal to 45 degrees, then both of those things are 1 over root 2. Then it's equal. Okay, so that's how we make cos theta sine theta bigger. Putting it all together, I want the biggest value is going to be, let's write it over here somewhere, is going to be less than or equal to the biggest value that it takes. Biggest value is going to be pi over 4 plus 1/2 over pi over 4 minus 1/2, plugging in the biggest value that cos theta sine theta can take, which is, I think, simplifying that a little bit, pi over 2 pi minus 2. Fantastic. Okay, it uses every previous part of the question. It's a really neat question in the end. Okay, personally I think, even if we hadn't done part 1, I think it's clear that you make as much of the floor as safe as possible just by making A really big. We just want to make A big. And you make A big by making cos theta sine theta big, which is what we were doing in part 3. Kind of that link. Maybe you didn't think about part 1. I think that's okay. Right, okay. Haven't done this before. This feels really sad. I have a question 6 in here as well. I have this question about truth and lie. I think we're not going to cover that on the live stream. I think we're running out of time on omissions stuff, and omission seems to be quite popular in this one, so I'm keen to talk about some of the omissions questions that have come up as well. And I'm going to leave question 6 as, I guess, a bonus question. We might briefly talk about it at the start of next live stream. Sorry, that's the first time that we haven't covered things on a worksheet. Okay,